Problem 962 features a bell crank, and the only thing missing is the design of the pin in the middle. Dimensions are as shown here. We have a force coming at 30 degrees down from the horizontal. In the book they call that F1. I'm simply going to call it C. I get confused with F1, F2, and so on. So there's another force down at the lower point coming up at 10 degrees. We call that A. And then there's the reaction here at the pin we call B. So we have locations A, B, and C. As for the dimensions, vertically from A to B, we have 25 millimeters. Vertically from B to C, we have 30 millimeters. Horizontally A to B, 10 millimeters. And from B to C is 40 millimeters. The question is, again, the design of this pin. It is given, aside from the dimensions, force angles, it is given that the material is a beryllium copper that has a yield strength equal to 1,000 megapascals. Also has an ultimate strength, but I will ignore that for now. The designation is C17200. It's also given that it's a round pin, which makes a lot of sense. So we need to find and specify diameter D at point B, the pin. Most of the work of this problem is actually statics. We need to find the force on the pin. Now, it's also given that the pin is in single shear. So we need to find the force on the pin, the area on the pin, and consider in single shear. And the loads are repeated, so that will affect our considerations. So let's do the statics on this. Now we have essentially a beam here, but the angled forces make it more complicated to analyze than if they were straight across and all vertical or all horizontal. But it's still quite doable. We need to break each of these forces into components. So this is CY, CX horizontally, AX, and AY. We need to sum the moments about a point. We need to solve for forces in certain directions. But first step we need to do is break the C into components. It's given that C is 3.6 kilonewtons. So I can take this C and break it into components. Cx equals C times cosine of the angle, 3.6 kilonewtons times cosine of negative 30 degrees, and it's 30 degrees below positive x-axis. That yields 3.12 kilonewtons, which makes sense. It's still positive. It's going to the right. Cy, C sine the angle is 3.6 kilonewtons times the sine of negative 30 degrees. And the sine of negative 30 degrees is negative 1/2, so that yields negative 1.80 kilonewtons. Now that we have Cy and Cx, we can take moments about point B, and one might say that that doesn't help us because we'll still have two unknowns in AY and AX. That's true, but remember that AY is A times the sine of the angle, and AX is A times the cosine of the angle. The angle we know. So what we really end up with is one unknown, the force A. We will sum the moments about point B, and then must equal 0. And we'll start with the A's. A times the cosine of theta A, this is all AX. And AX is 25 millimeters from point B. It's a horizontal force. We're looking for a vertical distance. 25 millimeters. And we're assuming it's positive. Gives it a counterclockwise motion. Counterclockwise moment. If positive. Next, we have a y. So that's going to be a sine theta a. And this is 10 millimeters horizontally around from point B, giving it a clockwise so I'll just have to erase sign there. And it's a clockwise moment, so it will be negative. AY sine theta A, AX is a cosine theta A, and this 10 degrees is exactly that, theta A. But we're not done. Also need to add to this moment the c's. So we have cx times, okay, its distance to point B is 30 millimeters. And that is we have to measure this clockwise movement. And add to that cy times 40 millimeters. Vertical distance, looking, it's a vertical force. Looking for a horizontal distance. And also doing a clockwise movement. Okay, so we have 0. So we have 0 equals A cosine 10 degrees times 25 millimeters minus A sine 10 degrees times 10 millimeters minus 3.12 times 30 millimeters. 1.80 kilonewtons times 40 millimeters. The minus sign for the 1.8 kilonewtons was removed after bringing this term out of the absolute value signs. Now I have one equation, one unknown. Simplify it here. 0 equals A. I'm going to take A out of the first two terms. Cosine 10 degrees times 25 millimeters minus sine of 10 degrees times 10 millimeters minus 93.53 kilonewton millimeters minus 72.0 kilonewton millimeters. Now I can put these terms on the left hand side, solve for what's inside here, and I can calculate for force at A. A is 6.32 kilonewtons. It can also be helpful to calculate AX into AY using these formulas that we have here. So AX, 6.32 kilonewtons times the cosine of 10 degrees, which yields 6.22 kilonewtons. AY 1.097 kilonewton. Now, we still need to find Bx and By. Well, really we need to find B. We'll use our other favorite equations to find it. Sum of the forces in the x direction equals 0, equals ax plus bx plus cx. So bx equals negative ax minus cx. Bx equals negative 6.22 kilonewtons minus 3.12 kilonewtons. So Bx equals negative 9.34 kilonewtons. Adding up the forces in the y direction, 0, we have AY plus BY plus CY. Likewise, BY equals negative AY minus CY. BY equals negative 1.097 kilonewtons minus a negative 1.80 kilonewtons. So By is 0.703 kilonewtons. Let's write that here. And Bx is and considering what we have going on here, we got two forces, A and C, that are mostly horizontal. C at about 3 kilonewtons, A at about 6 kilonewtons. Makes sense that B will be very horizontal to the left at around 9 kilonewtons. So this answer makes some sense. The total force of B using the Pythagorean theorem, bx squared plus by squared is 9.37 kilonewtons. That's the hard part. That's all the statics. Strength of materials part starts with understanding shear stress. Shear stress represented by tau is equal to the force applied over the area in shear. Well, we know what our material is, so we can figure out what our appropriate stress is. We just figured out our force. We just don't know the area in shear. So let's look at our stress. And this is a repeated load. A repeated load for shear, our design stress is equal to our yield stress divided by 2 and multiplied by a factor for repeated load of 4. So it's going to be 1/8 of our yield stress. Our yield stress is 1,000 megapascals. That is our yield strength. 8, with 125 megapascals. Going back to this equation, our required area will be force over our design stress, and our force is 9.37 kilonewtons. Design stress of 125 megapascals. That yields 74.96, well, got kilonewtons over megapascals. A newton per megapascal is actually square millimeters, and the K is 1,000, so we got 9,370 newtons over 125 megapascals. That gives us the 74.96 square millimeters. Well, this is simply the area, which is pi d squared over 4. So now we have to solve this for d, and our diameter ends up as 9.77 millimeters, and most likely you specify simply a 10 millimeter diameter. To recap, this was mostly a statics problem, going through finding the forces for C, then using moments about B, and recognizing that AX is A cosine of the angle, AY is A times sine of the angle. The angle is given as 10 degrees, so we really only had one unknown in this equation. In this equation, we eventually found out that unknown A boiled down to this. We found the components of A, and we plugged those back into summing the forces in the X and the Y, and finding the force of B here. Are there maybe simpler, more direct methods of finding that B? Yes, there are, but this one certainly works and can end up giving you components that can help depending on what the problem is. But we found this force B. Using that and the design stresses used for single shear in a repeated application, our required area ended up as about 75 square millimeters, but we needed to specify the actual diameter. So that's what we found is just under 10 millimeters, and that's what would be specified.